Fisher Technique Learning Factory 4.0 illustrates processes for a digitized smart factory, from delivering raw material to the finished product. Industry 4.0 applications can be tested and demonstrated using the simulation model that has already been set up. Digitization activities are simulated on a small scale and learned before they are used on a large scale. The training and simulation model demonstrates the process from the delivery, collection, and storing of the materials through the ordering and the manufacturing processes to delivering the finished product.
The training factory industry is controlled by a PLC controller, a Raspberry Pi as IoT gateway, and a TXT controller. The PLC program controls the individual modules of the factory. The program is written in structured text. The PLC communicates via the standard OPC UA protocol with the Raspberry Pi, which acts as an IoT gateway to connect the factory to any cloud. The program on the Raspberry Pi is implemented in Node-RED. In Node-RED, there is an additional local dashboard available, which can be adapted to your own needs. The Raspberry Pi also communicates with the TXT controller via the standard MQTT protocol, which in turn enables access to the Fisher Technique cloud. The program on the TXT controller is executed in CC++.
The sensor image data are used and monitored in the Fisher Technique cloud. The integrated WLAN router transmits factory process data to the cloud in real time. The data is presented on a web-based dashboard. 3 views are available: the customer view, supplier view, and production view. The views and data can be accessed using internet-enabled devices and can also be used remotely. The USB camera is controlled from the cloud and can view the entire factory. A sensor station measures air pressure, air quality, temperature, humidity, and brightness. The default process cycle begins with storing and identifying the material. Using RFID NFC technology ensures that the material can be digitally traced. The integrated NFC tag stores production data that can be read out via the RFID NFC module. The cloud displays the part's color and the ID number. The vacuum gripper places suction on the material and transports it safely to the high bay warehouse. The production view on the dashboard shows where the product is in the manufacturing process.
The first-in, first-out principle applies to outsourcing. The goods that were stored first are also the first to be removed.
Ordering material is triggered online on the dashboard. The desired product and the corresponding color are selected in the customer view and then placed in the shopping cart. Customer-specific production takes place in lot size 1. The production process is simulated in 2 steps. The suction gripper passes the material on from one step to the next. The material is transferred to the sorting system once production is complete. The sorting system receives the allocation command as soon as the color sorter detects the proper color. The material is sorted using pneumatic cylinders. The production data is written on the material at the end of the production process. The finished product will be provided for collection. Instructional material and the source code for the stored programs are available online. The Fisher Technique Learning Factory 4.0 is ideally suited for education and training in vocational schools and companies, for research and teaching in colleges and universities, for development projects in IT departments, for production planners, and for demonstrating in-house software solutions at trade shows and other corporate events. The customized storage and transport case is a worthwhile add-on.
Online programming occurs when the robot is online or in an operational mode. The two types of programming we will discuss here are teach-pendant programming and lead-through programming. A teach-pendant, also called a teach box, is a handheld control and programming unit connected to the robot via a cable. Teach pendants can be touchscreen, keyboard, joystick, or other computer interface. All typically have an emergency stop button since the robot is operating with the technician in the work envelope. More modern teach pendants can also be wireless. Teach pendant programming is a method by which the operator steps the robot through the program point by point by point while recording the coordinates for each point. The technician has the ability to send the robot to a desired position, inch or jog to adjust it, and then record the point. The technician may also change the speed since a low speed is usually required for careful positioning or while test running through a new or modified routine. ANSI standards recommend a speed of no more than 10 inches per second when programming. Once the technician has recorded and tested the program, the teach pendant is disconnected and the robot can operate the stored program at full speed. Teach pendant programming is often associated with controlled path and point-to-point control. Lead-through programming, which is typically associated with continuous path control, is a method by which the technician physically guides the computer through the desired program. This method, also called lead-through-the-nose programming, is used most often in spray paint and welding applications. It requires very little programming skills and allows experienced technicians to accomplish the work using the robot while the controller records each step. This method typically takes less time to accomplish than teach pendant programming. Online programs can typically be edited for speed, point error correction, and small modifications once the initial programming is complete. Advantages of online programming include ease of use, little or no programming skills required, and the speed at which a program can be created. The disadvantages of online programming are the requirement to shut down the production line while programming is occurring, and that the technician typically has to be in the work envelope while the robot is operating, which exposes him to greater risk of damage.
In this video I will demonstrate the workflow for the robots programming in SprutCam version 10. First of all, select the active machines, and I will select this cooker robot. Okay, I have it activated. The next question is how to calibrate the tool. Then you calibrate the tool on the robot. You take some numbers from the robot control, and you have to input these numbers in this position. This position defines the location of the spindle nose and so on. So I use mouse wheel to rotate the tool, and you can see how the spindle is changed. Okay, for example, my location is this one, and this one. Okay, So the spindle is calibrated and the data is inputted. I can do the same with the robot table here. The next I need to import the part I want to machine. I will machine this simple surface. Okay, I will scale it 2 times, little bit. Okay, so if I make machine visible, it is located inside my robot. Go to machining, and first of all I can define the workpiece setup. I activate it, and for example I can take and put it, okay, let me from top take and put it here, and take the arrow and put it here. Okay, it seems that the part is located on the table, but it's not the truth, because if I will change the table position, the part doesn't depend. So I need to define the current workpiece holder. In the current schema we have 2 places for the workpiece. Simple workpiece, it means end the table. Okay, right now I define that the part is located on the table, and I can define the local position of my part. For example, it will be located this way. So in this place I have to input exactly the same Euler angles and offsets that I take from calibration of the base on the robot. Okay, I input it. The next let me just create the new operation. I would like to create, for example, finishing morph operation. Okay, it will use this tool. I can change the tool diameter, for example, and morph operation needs 2 curves in the job assignment and machining surface. I say it will be surface for machining. Enable filter to input edges. This edge is the first curve, this edge is the second curve, and let me calculate the toolpath. Okay, toolpath is calculated, and we can see right now that let me simulate it. Okay, and we can see the singularities. Then tool is going. Perfect. How to? Okay, let me set change the angles just to make the not the angles. Let me change the step. 100%, and okay, and the next how to avoid the singularities here. We have this parameter in the in every operation: direct to point and fixed vector. For example, I can say fixed vector and say plus y and recalculate the toolpath. Okay, right now we can see the tool is located this way and machining going this way. I can change, for example, minus y and recalculate the toolpath. Right now we can see that the tool is located this way. Okay, I can, by default, I can use direct to point and define some point. What does it mean? So we have the magnet point and I can take this magnet and try to move it, and you can see that the tool is located to the nearest position to this magnet point. By default, the magnet point is located on the elbow point. Okay. Also, I can control the rotary table. Right now we had our motions without table motion, and I can enable, for example, external axis 1, this one, and external axis 2, this one. So if I enable rotate, for example, external axis 1, then I have to define the position of the rotary table, and I want to say that the tool axis must be located in positive Z. And what we can see right now, so the tool is looking up always. And let's watch the machining. I can change, for example, look on +Y and recalculate. So nothing changed because we need rotation of the second axis to do it. Let me check. Okay, and watch the result. The same. Okay, rotary table, tool axis. Maybe it's impossible to rotate. Yes, it's impossible. Okay, the next very interesting thing. For example, if my table is not rotated and I would like to machine a simple way, and I want to avoid the singularities here. Right now we don't see the singularities, and because the rotary director point is custom, go back to the elbow, and rotary table is not important for us. Yes, right now we have the singularities. Yes, this place. There is so-called axis map. It's the same like in the Robot Master, and I can click build map, and we can see this. So the horizontal axis of this graph, it's the length of toolpath, and the vertical axis is the rotation angle around the tool axis. And we can see that these zones go along these yellow zones go along the singularities. So the collisions, I can also calculate the collisions. It works exactly the same way like it works in Robot Master, but maybe a little bit faster, I think. Okay, so I can define my own way to go from the left to the right side of this graph, and by default I click build automatically, and by default right now it works perfect. I can take and move. So when I move, I press button up and button down on the keyboard, and you can see that the tool is located in the same point of toolpath, but rotation angle is changed. I can write this way any position as I want, or maybe this one, and apply the toolpath. So maybe it's not the perfect picture, but we can see in the simulation that it will work without any problems, because we work around all bad places. Okay, go back to this graph. I can also control axis C and two external axes. If I want, for example, change axis A, I can click build map. Also, let me disable collisions and okay, perfect. Right now the axis A is located on this 0, but I can, for example, put any way I want. Perfect. So when I change the position of my graph, you can see that the position of the table is changed. Perfect. So if I recalculate the toolpath, we will see the inclined table as well. Okay, so it's how to control the robot motions. And another very interesting thing, it's about first approach and retraction, but it will be in the next video. And the last position, we have to click postprocessor and select, for example, Fun KUKA robot postprocessor, calculate run, and we can see ready toolpath with external access as well. Thank you for your attention.